Чё-чё-чё? Что?
Влад снова сегодня не с нами, поэтому голос из-за экрана будет в моем исполнении.
Ага, хорошо.
В моей озвучке.
Так, так, добрый день. Так, я вот, значит, сейчас мы, или все равно нужно по-английски, да, потому что там кто-то смотрит телевизор. Хорошо, ну давайте.
Конечно, можем сказать,
Что уже все кончилось, да, и там. Не, ну в принципе, на самом деле, действительно, более-менее все кончилось. Я сегодня хотел просто привести, там, ну я сегодня я буду. Да.
Пока не
Да.
началось.
Черт, куда я сделал связь?
Вы говорили, что по поводу того, что нужно будет задать задачи, которые были в течение смены.
Ну, я не говорил, что письменно, я говорил, что лучше устно, наоборот. Но.
Вот, значит, первый вопрос, когда планируется дедлайн? И второй, если он на этих выходных, то можно ли сдвинуть?
Нет, по-моему, этот вопрос обсуждался, да, действительно, по-моему, мы уже договорились, что до следующей среды, да.
Я не помню конкретной даты.
Да. Ее, может быть, официально. Да, по-моему, действительно говорили. Где-то фигурирует.
Да, я просто не помню.
Где-то, да.
Слишком много дедлайнов на эти выходные выпадает, поэтому как-то грустно.
Ну да, нет, в общем, да. То есть совершенно нигде не утверждалось, что это должно быть писано, я бы сказал, что скорее устно.
Да. Подписано за крышу, я имею в виду.
Ну да, хорошо.
Подразумевалось.
Так, я вот только. Yeah, so you see, today I'm going I'm not going to prove much, yeah, so just to tell a lot and maybe to give some examples, but it's rather advertisement of some other things like number theory, so it's there will be not that many proofs. So roughly speaking, we are going to discuss the following question. So given some integer n, well, at least 2, we want to find the Galois group. Of the following polynomial x to the n minus x minus 1. And we consider this as a polynomial over the rational numbers. Yeah, so the question is what is its Galois group? So you see it's very particular thing. So of course you can say that if n is a prime number, yeah, then of course then what's the answer? Well, you don't. Well, at least you know that this polynomial is irreducible, yeah? But can you prove that it is irreducible for... Can you prove, by the way, that it is irreducible over Q, yeah? If n is...
Well, we had this theorem for finite fields. This doesn't seem to be interesting.
Oh, why not?
Okay, for example, let's take the reduction by any prime modulo.
Not any.
Modulo
Modulo z prime. You see? The point.
We assume that n is prime.
If we assume that n is prime, then you see that if it has, if it is reducible, then it is reducible over z, over the integers. And then you can reduce this modulo n. Yeah, so you get a splitting over. So you can consider this over a finite field, and you get a splitting, but it does not split over the finite field. Yeah. By the way, why?
So for finite fields, we have something like x to the nth minus x minus a, and then we got that if alpha is a root of this polynomial, then alpha plus 1 is also a root.
Okay. Yeah.
And then we got that also that alpha should be contained in our final field, and we assume that it's reducible.
Yeah.
So there was a problem.
Yeah. So it's So for So when n is a prime, then it's easy to show that it is irreducible. But in general, it's not that evident. Yeah. But it was shown some time ago by.
So we do the reduction by reduction modulo n.
No, it doesn't work. I mean, you see that.
So in case of prime n.
Yes, in case of prime n it works, but not in general. Yeah. So in general, it is due to Ernst Selmer. So it's Selmer. So it's 1956. So it is. Let's call it P maybe. So P of x is irreducible. Irreducible. So and how to prove this? The idea is maybe so. You see that there is certain inversion on the set of polynomials. Namely, you can reverse the coefficients. Yeah. So
It's reducible
over Q. Yeah. So notation. If we notation. Yeah. So if Q is a polynomial, doesn't matter over. So if Q is a polynomial of x, then we denote by Q tilde the polynomial with reversed. So if it is let us. So this will be a n x to
let's
the
just say that
m.
tilde is x to the dep of q by times q x inverse.
Yeah, so just reverse the order, and so the only subtlety is that if in principle it preserves the degree. Yeah, so this operation. So A naught. But the only subtlety is that it preserves the degree if the constant term is non-zero. Yeah. So but maybe so properties, some evident properties. Well, of course, it is this operation is multiplicative. So if we
so if q of x is polynomial, then q tilde, and then what about q tilde?
it is a polynomial,
Okay,
but its degree.
So here we just define q tilde.
Yeah. So this is definition. Yeah. This is definition. But what can we say about this operation? That of course it is how it's called. It's it is idempotent. Yeah. So it's if you no, it is no, it is inversion. Yeah. So if you apply it 2 times, then you come back to well, not really, but well. Not really, but well, there are some subtleties with subtleties depending on vanishing of this constant term. So degree of q tilde is the same as degree of q if if the constant term is not zero. Yeah. So it's Yeah. Now, so the properties are, so first of all, it is multiplicative. Well, of course, it is additive. Is it? Well, we don't care about additive properties. We care about, you see, we want to play with decompositions. Yeah, so we're only interested in multiplicative properties. So what we should say that the tilde of a product is a product of tildes. Yeah. Is that well? That should be evident from this definition. Yeah. So it's no problem here. Now, what do we want from this? We want we want first step one. Step one is the following. So we assume. So how we will use this operation? So we will apply this operation to to this polynomial, assuming that. So we will assume that it is decomposable into product of two polynomials, and so what we will get. So if maybe property, well, not that many properties, just one property. So if P is the product of two polynomials, then well, maybe I should say this later. Well, we will just play with this formula. Yeah. Next, what we want to do is the following. So we assume that. So let t of x. I write t instead of p just to make sure to stress that it's not. It works in general, not for this particular polynomial, but of course the applications will be to the case when t is p. So if yeah, so assume that t is a polynomial, well, with integral coefficients, but whose constant term is non-zero. Yeah, so it's not divisible by x. And we assume
Sure. X is a set or some polynomial?
x is a letter.
No.
Oh, спасибо, ага, спасибо. Спасибо. Yeah. Yeah. And we assume that it is coprime to t tilde, coprime with t tilde. Yeah, and now we assume that t is a product of two polynomials, p and q, and we assume that both of them are non-constant for non-constant polynomials in X. Okay. And then we can introduce. You see that we have so far we have two polynomials, non-constant polynomials. We consider the product of one of them and tilde of another one. Say p times q tilde. Okay. And the claim is that, so it's again a polynomial with integral coefficients, and the claim is that first of all, the product of t and t tilde is the product coincides with the product of S and the S tilde, and the second is that that S is not equal to plus minus t and plus minus t tilde. Yeah, so well, is this evident?
The first part.
Yeah.
It's obvious by the first property.
Yeah. So what is written here? What is written here? Yeah. So they are t and t prime are coprime. Yeah. So if
So we're about the second part.
yeah. So you see that what we have done. So what we can consider just. You see that all these cases are similar. Yeah. So we can consider just one of them. For instance, what would that mean? That S is equal to say T. Yeah. There is no big difference. Yeah. Between. Yeah. So this would mean that what is S? S is P Q tilde, and what is T? T is PQ. Yeah. PQ. And this would mean that, well, of course, we can forget this P. This would mean that Q coincides with Q tilde. Yeah. Well, we can write here plus minus, and it doesn't change anything. But this means that, what is this? This is a multiple of, this is a divisor. Q tilde is a divisor of what? Of T tilde. Yeah. And Q tilde, Q without tilde is a divisor of Q, of T. Yeah. So this would mean that T and T tilde are not coprime, yeah, because we assume that Q is a non-constant polynomial. Yeah, so that's more or less clear. Yeah, I hope so. Yeah. Next step. Next step, we assume that that this, so we apply this first step to our polynomial P. So we assume that P times P prime is equal to what? To something like S times T tilde. Yeah. Actually, we can. You see that this polynomial is monic, and therefore we may assume that S is monic as well. So where S is monic, well, let's compare.
Monic
Means that the highest, yeah, the highest coefficient is equal to 1. So, yeah. So what is S? S is some. Well, it's of course it is of degree n. Yes, so it is some a.
And here we assume that S tilde might not have the same degree as S.
No, because
so S is still some
polynomial.
Some polynomial from
Non-vanishing and zero, yeah. So with non-zero constant term.
It has to have a non-zero constant term if P has if P and P tilde have no.
Yeah. Otherwise, you see that otherwise it is divisible by some power of x, and this is not divisible by. Well, let's write down what is.
We say that P and S are correct.
No, you see that. That's a good question, but we have to check this. We have to check that
So
P.
here we take P from our.
This one. Yeah.
From here. P.
Yeah. Let's look at coefficient at x to the n. Don't know what is the coefficient of what, of s times s tilde. What is this?
It must be one.
Hmm?
And so still that it's the sum of zeros and first and minus first.
So it's sum of a I times a n minus I x to the nth.
And then the coefficient.
So the coefficient at x n to the nth is the sum of ai a n minus I.
Of what?
Аид и I минус y. Ну, произведение. Мы к этому
Yeah.
придем сейчас.
Yeah, exactly. Yeah, as Masha
Да,
says.
конечно.
Yeah, as Masha says, this is the sum of squares. Yeah. And but instead of s, we can take p. Yeah. So they should be the same. So what is that for p?
For P it's 3.
It's 3. Yeah. So the question is how many solutions do we have for this equation?
In integers or
In
in
radicals?
integers there are up to 8 solutions.
No. You see that our polynomial is monic.
Okay, then there are 4 solutions.
No, because the constant term is yes, you're right. Yes, you're right. But you see that we have
Okay. So the a to the nth must be.
yeah. So maybe we should write right. Yeah. So s is x to the n. Next.
Plus minus some x to the kth.
Yeah.
Where we don't know what k is.
Yeah, maybe we should write just aj plus a naught. Yeah, so where a naught and aj are some plus or minus 1. Yeah.
While a naught must be minus 1.
Why?
Because in p tilde the first coefficient is minus 1. So the coefficient at x to the nth is minus 1.
Well,
Сейчас при двойной минус первой степени будет коэффициент единицы, потому что это произведение двух крайних коэффициентов. Поэтому минус единица.
well, wait. Maybe we should write this more explicitly. So we write x minus 1 times minus x to the n minus x n minus 1 plus 1. So you say that yeah. And here we get so this is the same as x to the n plus aj xj plus a naught times a naught x to the n plus aj x n minus j. And by the way, j is between 1 and n, yeah? Plus a n. All right, so actually, I'm sorry, here is 1. Yeah, so you mean that a naught should be minus 1, yeah?
Yes.
Yeah, so a naught is minus 1. And what else can we say?
Then let's just dispose of the brackets and take a look at the coefficients. And then we can get a system of linear equations for AJ.
Yeah, so maybe we should make some assumption. Yeah, so first of all,
Not linear, but still.
yeah, so what is, so here, how many terms do we have here? We have x to the n.
X to the 2n minus x.
Yeah,
to the n.
yeah, x minus x. Next we have, what do we have? We have,
Minus x
yeah,
to the
actually,
2n
maybe we should assume that, you see that it's not interesting to assume that n is 2, yeah?
Okay, then let's assume it's at least 3.
Well, at least 3, yeah? Maybe even 4. Why not? Yeah, well,
Let's assume that it's at least 3.
yeah, at least 3. Just, you see, the point is that we have to know what is bigger, n plus 1 or to n minus 1.
For n, if n equals 3, then 2n minus 1 is already bigger than
Okay.
n plus 1.
Okay, great. So yeah, so here we have to n minus x to n minus 1 plus x plus x to the n plus 1. That's it? Yeah, I think yeah, plus 3 plus 3x to the n.
Yes, okay.
And it should be symmetric, yeah. So it's not interesting to write down the rest. It is symmetric because it is a product of it is a product of p and p tilde. So it's and the same for the product of s and the s tilde. So there is no point of writing more. Okay, so so here we have x. We already know that a naught is minus 1. So this will be minus again minus x to the to n. And here we have to make some guess what is what is bigger, n plus j or 2n.
We can, it's n minus j. So we have to get 2n minus 1 somehow.
Yeah, so this means that we can conclude that that either j is equal to 1 or j is equal to n minus 1. Yeah, this more or less corresponds to okay. Yeah, so you see that the point is that if j is 1, then you get more or less you get p. And if j is n minus 1, then you get p tilde. Okay, yeah, so mhm. Yeah, so j is yeah, so if j is 1, then what can we well, we can write this, of course, minus a j x n plus j this here minus a plus, yeah, plus aj x to n minus j. Yeah, so if j is equal to 1, then aj is minus 1, and if j is n minus 1, then it is then aj is 1. And j is 1. Okay, so you see that actually, yeah, so this means that that s, in the first case, s is just p, and in the second case, s is minus p tilde. And of course, this is a contradiction, yeah, because why this is a contradiction?
Because we assume.
Yeah. Yeah, because yeah, because this contradicts our this condition. Yeah. So it is irreducible. But now we want to calculate its Galois group, and so can we do that? Can we do that? Yeah. So to do that, we well, at least we know that this polynomial is irreducible, and therefore the Galois group should act transitively on the set of roots of this polynomial. Yeah, so we have to find a transitive subgroup in the symmetric group on n elements. And how could we do that? Yeah, so the point is, yeah, so there are several ideas, yeah, here. First of all, so the conclusion is, yeah, so the idea is the following: some group theoretic fact that so it's false. Okay. That a transitive subgroup, a transitive subgroup of the symmetric group generated by cycles of prime length or prime order and containing a transposition is the whole symmetric group. But actually, maybe I should shorten this formulation just by saying that generated by transpositions. Is the whole symmetric group. Yeah. So that's an exercise. I mean, we're not going to check this, but I have some reference, but reference is, but it is probably, I mean it is a standard reference, but I'm sure there are many other. So open Teil 1, Seite yeah, so and how we will
Петрович, а можно назад вернуться? Почему? То есть вы доказывали вроде как, что P не сложен, и предположили почему-то, что P с черточкой это стиль, это S на S стиль, и доказали, что так не
Ну, мы
бывает.
знаем,
yeah,
мы знаем, что у нас P и P с черточкой, ну, такие стили, они взаимно простые, просто проверяйте руками. Тогда
yeah,
получается...
you're right. You're right. We had to check. Formally speaking, we had to check that
Тогда мы, получается, мы предположили, что у нас P разложим. Когда мы взяли S такой же в первом свойстве, то есть мы взяли P, такое, что, ну, пусть у нас P это произведение некоторых, плохо сказал, пусть у нас P это произведение некоторых Q. Когда мы взяли за S R напустили, вот, мы знаем, что у нас
x
минус x лентой и плюс 1. Минус x лентой и плюс 1. Ну так тоже вариант. Вот. Короче, мы взяли, видимо, S таким вот, что это R напустили. Далее предположили, что... Далее мы знаем, что первый пункт у нас выполняется такое равенство. И второе, что если это так, то S у нас не плюс-минус T, не плюс-минус T тильда. А здесь мы получили обратно. То есть, что если у нас разложим, то возьмем такой многочлен, тогда и получим из этого всего части, что либо, ну, что S у нас попадает в числе запрещенных, так сказать.
yeah. So yeah, we just had to check that they are coprime, but you see, it should be more or less clear. Namely, you just replace the second one by the difference. Yes, so you get the difference is just x to the n minus 1 plus x. Yeah, plus x. So you can forget this x. So you can replace this by. So this is the difference, and of course these are coprime. Yeah, these are because x is coprime with this one, and here are you get just roots of unity, and well you can. It's not.
Which don't seem to be
Yeah.
roots of this.
Well, you can check it directly. You can just multiply. You can forget this x.
Well, we can just write the next iteration
Yes, you can forget this x.
because x is coprime with.
Yes, and then you can multiply this by x squared and subtract from that. So, well, actually, it's not maybe forget an x. Yeah, so when you multiply by x squared, subtract from this term, you get x squared plus x plus 1. And actually, it is important that you get something like this because this actually you can try to modify this proof for some other polynomials like this. Like this means when this not poly but trinomials. Yeah, you can try to prove something for other trinomials. Other trinomials with coefficients plus or minus 1. Yeah, so for instance, you can try to look at polynomials like this. And my question is that is that irreducible. Well, if you think a little bit, you will see that it is actually not irreducible in general, but because sometimes you see that when n is congruent to -1 modulo 3, then it has some evident roots like plus or minus cubic root of 1. Yeah, and therefore this polynomial is divisible by something like x squared minus x plus 1. But the point is that this is the only divisor, and so well, you can try to modify this, these arguments just to see what happens if these coefficients are slightly different. Okay, yeah, so the conclusion is that this is yeah, so we can yeah, so you see that we get that the greatest common divisor is coincides with the greatest common divisor of something like this and something like this, and sometimes they do have common divisors, yeah, but not in our case.
Perhaps it depends on n.
No, in our case not, but in if you modify this somehow, yeah, if you modify it somehow, then for instance put here plus instead of minus, then this this really depends on x. By the way, why they do not have? It's strange. Well, something wrong here, but yeah, but you see, it's no, it's definitely. How could this happen? Something wrong here.
What exactly is wrong? What exactly is wrong?
No, nothing wrong. I mean, yes, you're right. Nothing is wrong, because you see that here we have the cubic root of here the root is the cubic root of 1. Yeah. So if we put here cubic root of 1, we will.
Why the cubic root of 1 is the root of this polynomial?
Because
If you multiply this by x minus 1, you will get x cubed minus 1. Yeah, so yeah, but this is not a yeah. So the cubic root of 1 is not root of here. Yeah. So, but it would be root if this plus was minus. So it's okay. Right. Yeah. So yeah. So so our goal is to show that the Galois group is generated by certain transpositions, and the question is, so there are two questions. We have to get.
in fact, we say that it's generated by certain transpositions or
By some.
by all transpositions.
No, by some. So there are two. First of all, it is generated, and by transpositions. So.
Тогда можно сгенерировать, конечно, извиняюсь за мой английский, мы разве не можем Sn-1, например, сгенерировать в Sn, и тогда у нас, казалось бы, оно будет транзитивно.
Сейчас, у нас откуда, где S? Кто, подождите.
Сейчас.
Не, подождите.
Еще раз. Может, будем транзитивность?
Который, да, любой. Вот у нас есть n. Yeah, we have n roots of this polynomials, of this polynomial.
And у нас транзитивная подгруппа, это значит, что любой элемент из нее можно перевести в любой элемент из нее, так?
Любой с корней.
Она просто множится из элементов.
С корней. У нас есть we have n roots, n elements, and this action should be transitive. It means that all these elements form a single orbit. So we know that it is this action is transitive because the polynomial is irreducible, but we want to first of all to construct some transpositions, well, and to make sure that they really generate the whole group. Yeah. So here some arithmetics comes in play. So how would we prove that something? So first of all, where do these transpositions come from? They come from inertia subgroups. So the claim is that inertia subgroups of this Galois group consist of two elements, and therefore, well, and we need more. We need that they are really transpositions and not just elements of second order. Yeah. So we have to. So what does this mean? That we want to look at inertia. So by the way, should I remind you what is? We have not discussed this. What is inertia subgroup? No. Well, then I should remind you what. Do you remember what is a decomposition subgroup? Well, maybe I should remind you. So, so decomposition. So first of all, what is this about? Yeah. So this is. So we have a field extension, say a Galois field extension, a Galois extension, a Galois extension of fields, and we have say evaluation. Some topology, yeah. So V is maybe W, yeah. Evaluation of L, and then the decomposition subgroup, decomposition subgroup. Group denoted by dW is the stabilizer of this evaluation. Is the stabilizer of this evaluation. So this means that it consists of this Galois extension. Yeah. So it consists of all elements of the Galois group. L over K, such that these elements does not change valuation. So if you can apply this automorphism of L and then take valuation, and the result will be the same as you have not applied this valuation. This is the composition subgroup, and the inertia is yeah, so to define the inertia, we have to denote, again, notation, so notation, so we denote by OW is the valuation ring. So should I remind you what is evaluation? You can well, so evaluation is just so evaluation is just well, in our case, we can assume. Well, it is. You can think of this as a homomorphism from the multiplicative group to the totally ordered abelian group, such that non-Archimedean triangle inequality holds. So this means that the sum, so the value on the sum of x and y is at least the minimum of the values on x and y. Yeah, but in our concrete examples, this totally ordered group will be just the group of integers. So example, gamma is integers, and in this case, evaluation is called a discrete evaluation. Discrete evaluation. And sometimes we define this valuation also at 0. Yeah, so we say that the value of at 0 is denoted by this symbol, and this symbol is greater than any element of strictly bigger than any element of gamma. So that's we need this extension because I want to define the evaluation ring, and the evaluation ring is the set of all elements of the field where this evaluation is non-negative. So it's easy to check that this is a local ring, and actually evaluation ring. Evaluation ring means that any element in the fraction field either belongs to this ring or its inverse belongs to this ring. Well, roughly speaking, any element is non-negative or its opposite is non-negative. No, sorry, it's well, its valuation. Yeah, its valuation is either non-negative or the valuation of its inverse is non-negative. Yeah, so next you have to define the, you may define the maximal ideal. Here maximal ideal is just the set of all elements where valuation is strictly positive. And then you define the residue field. So residue field is just the quotient of the evaluation ring by the maximal ideal. And now we can define the following homomorphism. You see that let us denote, so let V be the restriction of W. So you see, we come back to our situation where L over K is a Galois extension. Then we can restrict our evaluation to the subfield K, and then this will be evaluation. So this is evaluation of K, and for V we can also define this this residue field, and then there is a natural homomorphism. Well, actually, there are two natural homomorphisms. Maybe, maybe. Well, let me. Yeah, maybe I should start with one homomorphism and continue with another one. so natural homomorphism from the decomposition subgroup to the Galois group. Of course, yeah, strictly speaking, we have to make some, it is a Galois extension, yeah, it is a Galois extension, it's okay. We have to check that this is a Galois extension, yeah, so, but let's try to do this. A kappa of W over kappa of V. Yeah, so the question is whether this is a Galois extension. What can you say? Yeah, so but anyway, so is there is a natural morphism, there is. So definition, its kernel is called the inertia subgroup. The inertia subgroup, inertia subgroup IW is the kernel. Of this homomorphism. How to check this? Yeah, maybe we should first of all it may make sense to redefine this in some other terms. Namely, you see that so far our situation is very general. Well, rather general, because we deal with certain very general evaluations, and it's not completely clear how to. Yeah. So probably it's not. It is false in such generality. But what we are actually going to do, we are going to deal with discrete valuations. And when you deal with discrete valuations, so. But anyway, you can. What you can do, you can replace here Galois group by just automorphisms. Yeah. So maybe we should write this more accurately. So we take here just automorphisms from the automorphisms of the residue field of W over residue fields of V, and this is well defined because you see that what does it mean that our what is the composition group? The composition group is something which preserves the valuation. And what does this mean? This means that any element of the decomposition group preserves the evaluation ring and the evaluation ideal, and therefore its action descends to the quotient. So this is you see that in a sense it is just to define. Let me this arrow is defined tautologically. So you have to so you take some alpha. So what is alpha? Alpha is an element of the residue field, and the residue field. What is this is the quotient of evaluation ring over the maximal over the evaluation ideal. Yeah. Then you just lift. So you can lift your alpha to the evaluation ring. And then you have an action of this decomposition group. So you write as here G alpha tilde, And you consider this G alpha tilde modulo the maximal ideal. And because you see that alpha tilde is defined uniquely modulo the maximal ideal. And the decomposition will preserve the maximal ideal. So this this G alpha tilde is well defined modulo the maximal ideal. And therefore it is well defined as an element of the residue field. Yeah, so this is modulo the maximal ideal. This evaluation ideal of V. And of course, this if alpha was in the residue field of V, if it came from the field K, the residue field of K, then of course this action is identical.
I'm opposed to G alpha tilde.
G alpha tilde, yeah, modulo the maximal ideal.
So what's alpha tilde again?
Alpha tilde, you just this is just a lift. You start. Alpha is an element of the residue field. You lift it. Consider a representative of alpha in the evaluation ring. Then you have an action of your group on the. Should I write this more?
No, it's G kappa W.
Cup of W over. You see that this is just an automorphism. You see that I replaced the Galois group. So far we don't know that this is a Galois group, because it's not evident that this.
Where did we get kappa of V from?
Kappa of V, because this is the claim that the action on this subfield is identical.
Okay, so okay, see where did we get V from?
Okay. Yeah. So the question is, what does inertia control? Yeah. So what is the meaning of the inertia? And the answer is that it controls ramification. So it's so if there is no ramification, then this homomorphism is injective. Ветвление. Yeah.
Просто все-таки обсудить, что такое ramification, потому что я слышала про это на нескольких курсах и до сих пор не понимаю.
Ramification, yeah. So what is a ramification? Is
Сейчас на русском какое оно будет?
ветвление. Unfortunately, in Russian, there is only one word, ветвление. But in English, we have ramification and branching. So branching is what happens downstairs, and ramification is what is going on upstairs. So it's. Достаточно? Yeah. So ramification. Ramification is. So you see that so far we don't really need the Galois extension, just some maybe finite extension or algebraic, maybe finite. So let ramification. So we assume that L of K is a finite extension. and V. Yeah, and we have this. Yeah, we have. I just repeat this that we have evaluation L to the gamma. Yeah, maybe. Maybe we can assume that it is surjective. Yeah, and so we say that. Yeah, so we say that maybe there are, you can say that something is ramified. Yeah, maybe let me denote by V. Just as before, we denote by V the restriction of W to K. And then we say that V is ramified. V is ramified. If so, you see that when so what do we have? We have the following picture. We have the group of values of V. So if if V of K star is not equal, so in general it is a subgroup, but we say that it is that the evaluation is ramified if the group of values is of W is strictly bigger than the group of values of V. So, so the examples you should have in mind are the following. So, for instance, can you give me an example of evaluation? Модуль. Okay, yeah. Yeah, okay, so it's, yeah, so what you're saying is order of 0 at 0. Order of 0 at 0. Yeah, so, yeah, so example, so we consider.
Голос с другой стороны экрана говорит, что это классическая корреляция или как?
Да, нормирование, да.
Примерно куб.
Да. Можно, да, можно так. Окей, можно так. Yeah, so so there are two. Yeah, so far we have two examples. Yeah, so we have so F field, and we consider K, which is the field of rational functions. So rational functions over F, and valuation. So what is V? V is yeah, it sends x to 1, and any irreducible polynomial which is not x sends to 0. Yeah, so this valuation is uniquely determined by these two conditions. Что же вы имели в виду? Дробь. Так. Да. Ну, а это и есть оно. Это, нет, это вот вы говорите, what you're talking about is precisely what is written here. Yeah, I should say that this is so this is a homomorphism from K star to Z. So this is a homomorphism. I'm sorry, I forgot to say this is a homomorphism. Yeah, evolution is a homomorphism. Homomorphism. You see that you are talking, you are saying that you present your rational function as something, as a power of x, and the product of, and you have something in the numerator which is non-vanishing at 0, and so you just forget this. You just forget this and keep track only of powers of x.
И там еще уже наряду равно все части продолжить.
Yeah, that's completion. That's what I was going to say when I told that there is another. Yes, but it's completion. Yeah. So this is first example. So this is first example, and the second example, as Vladislav suggested. Yeah, to look at the same example, but we take k is q. Sorry, it's not an example. This is just evaluation, but we need an example. An example. Or non-ramification of an extension. So yeah. So now the first question was what is evaluation? An example of evaluation. The second question is an example of an extension, of a finite extension. Can you give some example of an extension of this field?
Extension of f over k.
Of k. We don't know anything about f. We don't care. Sorry, I forgot to say that we assume that the valuation is 0 on f. So yeah. So what? That's too much. Too much in the sense that too much, and this gives us strictly nothing because this is just a completion. So it's completion with respect to this valuation.
Ну, голос по ту сторону говорит, что если расширить поле скаляров f алгебраично. Но если не алгебраично...
No, we don't...
Если f не алгебраично сам.
Okay, yes. Yes, so that's an example of unramified. Yeah, so if E is is an algebraic extension, in an algebraic extension, and L is the some kind of just the field of rational functions, then we can extend the same way. Yeah.
Maybe it's E of x.
Yeah. Thank you. Then W is defined similarly. So it is, for instance, it is 0 on E. Yeah. Then V is unramified. Okay, but maybe more examples.
So what do you mean by completed evaluation?
Complete, yeah. Do you know what is a completion? So that's it. You see that it's when you have a discrete evaluation like this. Actually, when you have any evaluation, so let me. Вот это уже интереснее. Давайте, может быть, сначала. Wait, maybe we should first add the square root of. Что? Что? Yeah, completion, you know, topological completion. Yeah, wait. So you see that when so let me say one thing. So if we have evaluation, so if V or W, if V is evaluation with values in where in real numbers, then our field becomes a metric space. And if this is a metric space, then we know what is the completion of a metric space. So for instance, here we do have a situation like that. If we, for any discrete valuation, makes a field into a metric space, and therefore you can complete it. In this case, what you get is the Laurent polynomials. Series, Laurent series. So if n, then the completion KV is defined. Closure. It's nothing. It has nothing to. It has nothing to do with algebraic closure. Is defined. So the completion. And actually, maybe I should. Yeah, that's a good point to say that actually, what is the decomposition group? Пополнение. Подождите, вы на первом пополнение метрического пространства последовательности Каши с точностью до эквивалентности. Yeah, so and actually what you can show that so that it's a claim that what is the decomposition group? The decomposition group is just the group of automorphisms of the completion of L with respect to this W, automorphism over the completion of K. Yeah, so that's. So you see that actually what we do is we deal with these decomposition groups are just Galois groups of certain local fields. Yeah. So now, coming back to extensions. Yeah. So for instance, So Vladislav suggested to add the square root of x, but let us add the square root of if L is obtained by adding square root of 1 plus x. So the question is how to extend valuation to this field. No, because you see, actually, the point is, as you said, you see that we actually can look only to look at the completion. And if you look at the completion, then you see that actually nothing happened. Yeah. So what is the completion of this? So KV is. Совершенно верно. So let us first know that completion of K is just the field of Laurent series, yeah? F of x. And therefore, if what? If it is maybe to rest on the safe side. So if characteristic is yes, as then this field already contains the square root of 1 plus x. If characteristic is 0. I'm not sure if, yeah, well, maybe it's safer to assume that it is characteristic 0, yeah, but even without completion, so the conclusion is that you see that the conclusion is that these already decomposition group is already decomposition group is trivial, yeah, I think so, yeah. So yeah, now what happens if we add the square root of x? Well, it's clear, yeah? We have to define the valuation of square root of x.
So how we define the relation for the square root of 1 plus x? So
It is 0. Because it is, you see that it is, when you think of this as a formal series,
да, то есть мы как бы расширили наше поле, ну, в смысле,
пополнили,
посмотрели на эту штуку в расширении нашего поля.
пополнение. В расширении. Вы имеете в виду здесь?
Да,
Здесь. Yes, actually, yes, you can try to, you just try to, try to extend this valuation. So actually there are, there is some hint here. Namely, you should think of, especially when you deal with something like this, like curves, yeah, so, which is, you see there's only one variable, yeah, so it's a curve, and it's a function field of a curve. And when you deal with curves, then you think of valuations as points. And it makes sense because actually you can show that, so maybe I should write this somewhere, that maybe we should make this exercise. Make this exercise that any the exercise is to describe all discrete. Well, maybe it's not even discrete because they will be automatically discrete. All valuations of this field vanishing on the constants. Yeah. So describe all valuations v on f of x vanishing on the constants on f. So, and what I'm saying that if we deal with well, of course there is a zero valuation, yeah, but it's not interesting. But except of zero, the valuations are parameterized by the projective line over f. But you have to make precise, what does it mean projective line? Line. Проективная прямая. So, параметризует нормирование этого поля. So, you see, do you know what is a projective line? Are you sure? You sure? Yeah, but you see that there are some points that you cannot. For instance, what is the projective? How do you think of projective line over real numbers? No, there are some points that you cannot see on this picture. For instance, you see, you should think of, for instance, let us start with the affine line. What is the affine line? Well, a projective line, it's easy because if you know what is an affine line, because a projective line is you just have to glue two copies of affine line. So you take you have a map from well, you have affine line without zero, and you map it when z goes. So you glue two parts of. You see, you have to glue together two parts, two affine parts of projective line. But first of all, you have to know what is the affine line. What is the affine line? No, so actually the affine line is certain. Well, it is a topological space, yeah. So it is its closed points are irreducible monic irreducible polynomials. Well, prime ideals in the ring of polynomials, yeah. And the prime ideals, what are the prime ideals? No, how to describe them? How to describe prime ideals in the ring of polynomials over a field? Yeah, say monic, yeah, because you don't want to this. Ноль еще есть. Ноль. Ноль. Ну. Да.
У нас главные, получается, идеалы.
Все. Они все главные.
Это порожденные
одним элементом.
Одним элементом?
Да.
Сейчас, а простые идеалы тогда?
Prime ideals are those that the quotient by them is domain. Нет, это максимально. Целостности. Yeah. So you see the point here is that and how do you define? So what is the relation between? So in this case, in the case of this relation, this is just the ideal generated by x. But instead of ideal generated by x, we can take x minus a. Yeah, we can take any irreducible polynomial here. So let us call it p. So p is an irreducible polynomial. Irreducible polynomial. We can say monic. Yeah, irreducible. Irreducible monic. And here we say that valuation of any other monic polynomial, any irreducible monic polynomial is 0. Yeah, so the same way, because you have unique factorization. Yeah, so you can as you said, when you present it as a product of something like x or any other polynomial p, and the rest. And so then the rest, on the rest you say that the valuation is 0. And yeah, and actually, and you may ask, in the case of projective line, you have also infinity, yeah? So a point at infinity. So can you say what corresponds to the infinity? Where is the infinite point of valuation? What is that? Yeah, you see that so far, when we deal with irreducible monic polynomials and the corresponding valuations like this, you can put here p, yeah? So this corresponds to the affine part, but we deal with a projective line, so there should be some valuation corresponding to the infinite point at infinity. So what is that? Hmm? 0 is x. You see, for instance, when when p is x minus a, this corresponds to the point a. For instance, a may be 0. Yeah? But the question is, what corresponds to the infinity?
Сейчас можете конструкцию объяснить? Там еще и
Каким образом вообще афины...
так, тут голос с той стороны.
Да.
Значит, цитата. То есть нужно сказать, что relation ring это f от x или f от единицы на x. И рассмотреть простые идеалы. Infinite point это степень.
Yeah, that's right. Yeah, so the point was, yeah, so what was actually, you see that what was our projective line? So projective line is the union of something, well,
Я, кажется, не очень понимаю конструкцию. То есть мы как-то перескочили на комплексную плоскость с...
почему комплексная?
Ну, хорошо, не комплексную плоскость в любом случае. Как у нас... То есть что произошло, что мы x на x минус a можем спокойно заменить?
Well, you play the same game, so you want to define the valuation. So the question, how do you define it? Any rational function is a product of irreducible polynomials, yeah? In certain powers, possibly in negative degrees, yeah? And so you just decompose it and set your valuation to be 0 on everything except
For some reducible polynomial.
Yeah.
And about the points?
yeah, and the question is, yeah, so but the point is that that irreducible monic polynomials correspond to, so what actually we want? We want that we don't really deal with polynomials themselves, but rather with ideals that they generate. Yeah? And the ideals are precisely points. So these are prime ideals.
How are prime ideals points in the affine line?
You see that x is the coordinate on the affine line, and then your point is determined by. So, for instance, when you you want your well to annihilate this ideal, you have to send x to certain number.
So we're talking about an algebraic closed field.
Yes. But if we are not over an algebraically closed field, then we still can send it to some extension, yeah? but there will be more options, and as a result, so what actually what you do, you consider your polynomial, the whole ring of polynomials modulo certain prime ideal, and you can say that you consider these are points in values in an extension of this field F. So you can say that you consider points with values in in algebraic closure, but of course here the option is to choose several. Yeah, you see that when your polynomial is of degree higher than 1, and you have more options. You can send x to not necessarily to a unique element of f bar, but to several ones. So so they are also points, but which are not visible over the base field. Okay, yeah. So, but coming back to our example, yeah. So we, yeah. So why did I tell about this picture? Because when how could you look at this extension? So this the original field, you think of it as a projective plane, well, or maybe we don't really care about the whole. You see that we live in a neighborhood of 0. If our coming back to our example with this one, yeah. We actually live around 0. Yeah, so we only care about this valuation, which corresponds to point 0 on the affine line. Yeah, so actually we may think of this not necessarily projective, just affine line. And what is this extension? This extension is a curve. You can think of this as y, yeah, so for instance you can think of this as y equal, y square equals to x, yeah, so this is how it's called, parabola, yeah, parabola. Yeah, and inclusion of these fields corresponds to the projection. And so you see that as I said, valuations are points, and over more or less all points you can find 2 points, except of this one. And if you look at formal definition, if you look, where is it? It's here. Yeah, it's here. Yeah, we have to extend. Yeah, we have to extend our valuation to this extension. Yeah, to this L. How could we do that? How to extend the valuation to?
The square root of x should be either 1 or minus 1. Should be a square root of 1.
No. So yeah, you see that we have. We can look at. For instance, we can. Well, we may pass to completion, yeah. So actually, we can say that. So what is the completion of? We know that that the completion is just of k is just the form is the Laurent series over x. But what is the completion of? What happens if we add square root of x? Well, it will be just Laurent series in square root of x, yeah. So it will be, and then how? So the question is, how could we define valuation of square root of x.
If we have x, valuation of x is 1,
Yes.
then is the additive group. We have to have valuation of square root of x is 1/2.
Yes, of course. Yes, so 1/2, and therefore, and the rest is clear, yeah, because you present any Laurent series you present as a product of power of x, half integer power of x, and something invertible, yeah, something starting from some power series with a non-zero constant term, yeah. So it's and so the conclusion is that the group of values of W is 1/2 is the group of half integers. Yeah, so it is strictly bigger. It is bigger. So the our original valuation group is the index 2. So maybe I should call that should add to here that it is called the ramification index. So so this index so we say that the index of this group of the original group in the new one is called the ramification index. So is the ramification index. Index. So, and in this case, it is this ramification index is 2. Okay, yeah. So now coming to is there was suggestion by Владислав to look at.
Тут вот вопрос
Да.
с другой стороны.
Да.
В данном случае индекс открытия говорит, что точка слоя стала в 2 раза меньше. Это верно в общем случае?
No, because you see that it may happen that you have you may have a ramification like this, for instance, like this. But maybe depends. If this is a Galois extension, then yes. But if it is not, then no, because in non-Galois case you may have something like this. But in Galois case, everything is a Galois orbit.
Сейчас, извините, как мы вот пришли к таким кривым, видимо, я немного...
Ну, правда, откуда взялась кривая? Почему мы не имеем права рисовать кривую, говоря про кривую?
То есть у нас откуда-то взялась кривая, и, то есть, точнее, я пока что не очень понимаю, откуда взялась кривая.
Yeah. So the question is where do these curves come from? Yeah, you see that there are two curves. There is a curve downstairs and there is a curve upstairs. So my question is it clear where the curve from downstairs come from?
What is downstairs?
Downstairs means corresponding to K. So you see that everywhere here we deal with finite field extensions. Yeah. So so in case yeah. So for instance, in this example, we deal with rational functions in one variable over a certain field f. Yeah. So the claim. So maybe we should start with this exercise.
Еще пока у нас ничего новый вопрос, опять же, с той стороны. Что означает быть расширением Galois с точки зрения геометрии?
Это быть накрытием Galois вне точек зрения. Накрытие. Что такое накрытие? Знаете? Значит, so,
Если там очень долго и сложная история, то я думаю, можно вообще попросить сейчас сделать перерыв пока?
хорошо, давайте. Break. 10 minutes break.
Трансляцию не остановлю, просто... Я просто отключу и все. Не надо ничего там делать. Просто ничего не надо, я это... Раз. Можешь проверить? Раз.
Ага. Так, на чем мы там остановились? Мы...
Там еще несколько вопросов.
Да.
Сейчас давайте зачитаем. Значит, еще такой вопрос. Видимо, быть накрытием Galois равно быть неразветвленным расширением Galois, в смысле как полей. В случае, когда есть точки ветвления, что мы имеем в виду под тем, чтобы быть накрытием Galois вне этих точек?
Ну, выкинуть все ветвление. Нет, ну тут...
Там продолжение, значит, идет рассуждение. Ну, нужно просто смотреть на соответствующее открытое подмножество кривой.
Ну, конечно. Да.
Я ограничу проекцию.
Да.
И вопрос, что там за поле получается на этом открытом множестве.
В смысле? Поле-то оно от открытого множества не зависит. В смысле, кольцо или там? Не, ну просто можно же... you see, if you have... there is a notion of Ramified cover, yeah. So, but you can just throw away all ramification, and you will get something unramified. But yeah. So yeah, but maybe we should come back to our ramification. Yeah. So what I was going to say that it is certain. Yeah. So what I'm going to say is that yeah, we have to say what do inertia subgroup generate in any extension. Yeah. So that's our interest. So maybe I should. Yeah. Maybe. We have not finished this exercise. Yeah. So. Oh, by the way, who knows what is Ostrovsky theorem? Островского. Да. Знаете, да? Маша?
Я слышала, я ничего не поняла.
А.
Ну, я знаю только формулировку.
Ага.
Я слышала формулировку, я ничего не поняла.
Я не помню, если честно, вроде что-то слышал такое.
Okay. Well, then we will do this exercise, and you will do the proof Ostrovsky theorem by yourself. Yeah. So let's do this, and there is not much difference between this and the Ostrovsky theorem. Yeah. So we want to describe all. By the way, who understood what was said about what Vladislav said about infinite point? Which valuation corresponds to the infinite point? So it's actually instead of Laurent series in X, you can consider Laurent series in 1 over X. In other words, you can so maybe we don't have much place here. Just so the infinity is just degree. Well, maybe we should write this way. So if P, Q and S, Q and R are polynomials, then this is degree. So these are polynomials in F. Then we can take the difference of their degrees. Yeah. so that degree of so degree of R minus degree of R minus degree of Q. So this is and when you, for instance, you see that the point is that valuation of 1 over x is 1, and is that correct? So this, and so the claim is that this is the complete list of valuations. So we have valuation corresponding to each monically reducible polynomial. We have and we have this one. And the claim is that that's the complete list. So can you prove this? So the condition is that this valuation is 0 on the ground field. Okay. So well, here I only have the proof of Островский theorem. Мы хотим или не хотим описать все нормирования полирациональных функций от одной переменной. А теорема Островского,
Для чего она нам?
она не для чего, она на ту же тему. Ну да. Что, это все меняет?
Ладно, просто, скажем так, нам, скажем так, термины, которые по-русски знакомы, по-английски могут звучать незнакомы, вызывается очень много вопросов, слишком много вопросов. Вот, потому что мы это все изучали, но или будем изучать в случае некоторых здесь присутствующих, получается, на русском в основном.
Yeah, so let's see. So how do you prove Островский theorem?
Там еще
Да, что?
с другой стороны.
Да, что там?
Мы можем попробовать сказать, что valuation ring должен быть обязательно f от x или f от 1 делить на x, то есть это должен быть.
Сейчас не понял.
Давайте я просто вам покажу.
Ну это же неправда. Это вообще не valuation. Valuation ring. Сейчас, Владислав. Valuation ring, это он хотя бы локальным должен быть. То есть, в смысле, оно, кольцо. Any valuation ring is local. Yeah? So polynomials is not a local ring. So, for instance, here, when we deal with such valuation, then valuation ring consists of all rational functions with no p in the denominator. Yeah, so that's the point. So you can p is allowed to appear in the numerator, but not in the denominator. That's the local ring. Sorry, that's the not. Well, it of course in our case local and valuation is the same actually. That's the point. Because что? Все нормально? Yeah, but actually, but anyway, it's a good point. So you see that instead of valuations, we can try to find valuation rings. Yeah. And
Владислав предлагает поправить и сказать, что это локализация вот этого кольца.
хорошо. Yeah, that's good. That's good. Evaluations, yes, that's true, but how to prove this?
Можно вообще, что такое локальное кольцо?
A local ring is a ring with a unique maximal ideal. Periodic integers, periodic integers. P generated by P. Or formal, you mean local ring. Local ring, you can take, for instance, any power series in several variables. This is also a local ring. You see? What is the maximal ideal here? Да, совершенно верно. Yeah, that's right. Yeah, generated by this x1 and so on. Yeah. And you see that actually it is maximal ideal because if it is not in, if an element is not in this in the ideal generated by x1 and so on, then it has a non-zero constant term, and therefore it is invertible. Yeah. So it's yeah, but it's you see that it's more complicated. In our case, everything is much simpler because we have only one variable, and that's the point. So because if we had 2 points, 2 variables, then the situation will be much more complicated. Yeah, so okay, we just have to, but you see, we can look at all possible, we'll just consider all irreducible polynomials, yeah, for say monic, and then we can try to look at options, yeah. So we have evaluation, yeah. Evaluation V, and well, it should be non-zero at least on one irreducible polynomial, yeah. Otherwise, it will be 0. Well, I mean, it's we don't we assume that it is not 0, yeah. So so there exists P, so irreducible, well, monic, for instance. Monic doesn't matter. Monic such that V at P is say 1, yeah? 1, well, it doesn't matter. 1. Well, doesn't matter, maybe 2 or 3, but not 0. So the question is, can it happen that V of Q, so now Q is another one, now Q is not P. Can it happen that yeah, sorry. I should look at yeah, I'm sorry. We have to. I'm looking at the proof of Ostrovsky theorem. So can it happen that that there are? So you see that we have to distinguish two cases. Yeah, so what happens if Q is so can this valuation be positive for some other Q, for instance? Can this happen? Can this happen? Yes. So you see, so what are the options? So if we know that in our examples, all at least in this case, in the case of finite points, yeah, finite valuations corresponding to finite points, this valuation vanishes on all irreducible polynomials except one. Yeah. And what happens in the case of this? In the case of infinite. In the case of infinite, it is just it is negative on any polynomial. Yeah. So we have to consider. Yeah. So maybe we should. Yeah. So maybe we should consider two cases when. Yeah. Maybe two cases. If well, I'm trying to imitate the proof of Ostrovsky theorem. So in the proof of Ostrovsky theorem, there are two cases. The first case when there exists P where V of P is negative, and everything is V of P is non-negative for all P. Yeah. So okay, and so what is the so how do we prove? For instance, here, what do? We
there exists such P that the valuation
is negative.
is negative, and do we have any regulations on like it's reducible or something like that? Or
Well, it doesn't matter because if
and also in the previous part, we say that valuation of Q is
yeah. So far, no,
for any Q.
no. You see, you see.
Just remembered, Ostrovsky theorem talks about not zero being like doing, but one. Because Ostrovsky theorem.
Yeah, but you see that in Ostrovsky theorem, valuations are written in a multiplicative form. So they are like absolute values. So and yeah, and their condition is this triangle inequality is weaker. Yeah, it's a usual triangle inequality, not necessarily non-Archimedean one. Yeah, so it's in a sense it is stronger compared to.
So what we did right now, we took like Ostrovsky theorem and we said we're ready for the
Yeah. Okay. Yeah. So. So what could we do is just to mimic the proof of Ostrovsky theorem. So can you? Oh, should I remind you the proof of Ostrovsky theorem? Should I or you? you can do this by yourself. Hmm? Okay. Yeah, but we need.
So here, and the second part, короче, вопрос. У нас все-таки на P какие-то ограничения есть, или у нас просто произвольный P в теореме Островского?
Actually, in Ostrovsky theorem, conditions are weaker. So in Ostrovsky theorem, so you consider what are called absolute values. So absolute values from Q, from Q to
So consider that
to R.
Our evaluation is
It's like a logarithm, but here we use usual triangle inequality. So x plus y should be bounded by the sum. So this is a homomorphism. So this strictly.
What does it look like? It's just
A homomorphism.
у нас это просто обычный алгоритм. Или как?
No, it's normal.
Ну, имеется в виду, что она какой вид имеет у нас?
Well, you mean answer, or you mean you want an answer, or you want a formulation?
I want first of all, I want to understand what are the conditions of
Yeah. So
for such.
so we want. You see that we want a homomorphism from the multiplicative group of the rationals to the multiplicative of positive reals. Yeah, satisfying the triangle inequality, and that's it. Ну, речь шла, там Маша имела в виду, что это нормирование, это логарифм вот такого. В случае, когда неравенство такое более сильное. Yeah, because you see that in case of well, in principle, this is also you don't really need to yeah, actually we don't really need to assume that this is yeah, this is also yes, this is also a totally ordered group, and so you can just consider this as gamma, but the only you see the difference. The difference is that here in abstract group we have only one operation, but here this plus we don't have this plus in an abstract group. In abstract group we have something like multiplication, but not this plus. And instead of plus, we use minimum, maximum, something like this. Okay, so yeah, so what happens if there is? So you see that if there is such a polynomial with negative valuation, then we want to get to conclude that this is an infinite valuation. So how could we do that?
Еще там с той стороны экрана поступает предложение перейти на подгруппу инерции. Как-нибудь. Ну вот там когда-то, сейчас скажу точно.
Ну хорошо. В смысле, что не отвлекаться на это? Ну хорошо.
Да.
Ладно, тогда я. So.
Поступает предложение, я, конечно, не эксперт. Народ требует лево.
Чего нужно? Хорошо, ладно. Okay, so then we will leave this as an exercise on Ostrovsky. So on Ostrovsky theorem, and and its variations.
У нас, да, вроде норма должна быть не отрицательной.
Чё?
Норма же вроде обычно не
Ну,
отрицательная.
отрицательная норма это как раз мультипликативная норма. Это как раз то, что все время...
Нет, ну это то, что Маша говорит, что надо логарифм взять. Если
Чисто в аксиомах, ну, в смысле...
в аксиомах считайте, что отрицательно значит меньше единицы. Так, значит, хорошо, да, значит, yeah, so coming back to, so this we will try to discuss examples, yeah, so coming to back to inertia, so the thing I have to say is that, so what is the invariance of inertia? So you see that we have defined this inertia subgroup. And the question is, here is our setting. It is, yeah, so our setting is here. So L over K is a Galois extension, and we have a decomposition group. So what happens, claim? What happens if we take invariance? So L invariance of inertia is, so the claim is that invariance of inertia is unramified over, at V, yeah, so at V, which is V, which is restriction of W to K, yeah? It is, you see that it is essentially what does this, where this come from? This simply means that we we pass to certain field, so we pass to the quotient of this group. So, well, some, it's not a proof, but maybe some explanation, and that this, well, we can pass to the completion, yes, so W over K V is, so what we do is, you see that when we pass to the invariance, then this means that we, well, actually this is a proof, yeah, so it's, why not, proof. So when we pass to invariance, it means that that the Galois group of these extensions becomes the quotient, yeah, so this EW, yeah, so and we know that this is the Galois group of the extension of the residue fields. So and yeah, so and therefore, well, anyway, even if we don't know that it is an isomorphism, it is embedded, yeah, it is embedded by definition, because it is embedded into the Galois group of the residue fields. Well, and therefore, yes, and therefore this means that our, for instance, degree of this extension is, so this extension is obtained by extending the residue field. So we don't change the evaluation group. So we don't. You see that we don't. We keep this uniform, what is called uniformizer, an element whose valuation is the generator of the maximal ideal in the valuation ring. Yeah, maybe this is just an explanation, not a complete proof. So just okay. So yeah. Now what happens if we look at all inertia subgroups? Then so maybe a corollary. Yeah? Corollary. Corollary is that if H is generated, well, if we have, well, maybe it's if H is generated by several or all inertia subgroups, then well, I mean, what I'm writing is some kind of tautology. Yeah, so it's that if it is not if it is generated by several subgroups, then it is unramified. It is so then it is the fixed subfield. The fixed subfield is then the fixed subfield is unramified over all
How is there several
several, I mean, actually what we are going to do, we are going to consider all ramified points. Yeah, so yeah, we are going to, actually we are going to deal with Ostrovsky theorem. So with Q.
Where did
And
you get that S?
Any S, just any set. Any set of valuations.
Set of what?
Valuations, yeah. For some set of valuations. Yes.
Значит, вопрос от Владислава. Он не понял, почему расширение не разветвленное, если его группа автоморфизмов вполне не совпадает с группой автоморфизмов Ровинский Fields.
The point is that you can think of elements of the completion as formal series. It's like sequences of digits. And digits you fix a representative of the residue field in yes, you fix a representative of the residue field in the completion and write down all elements of the completion as a formal series with these digits in uniformizer of this completion. So if yes, if so, for instance, it's sufficient to look at the first approximation. So if we if Yeah, maybe we should. Yeah, so suppose that big pi is a uniformizer of L. The generator of the maximal ideal of the evaluation ideal, and small pi is a uniformizer of KV. Yeah. So okay. We have. Yeah. So we assume. Yeah, we assume that our group is embedded into the Galois group of the residue field. Yeah. So that's the question. Yeah. So. Yeah, so actually you can, it is more or less equivalent to P, big P to the E, where E is the ramification index. And then, yeah, so we just have to, so yeah, so there is an element, so assuming that it is, so if E, so if there is a ramification, then there is an element in the group, well, G, well, L W E W over KV, such that G big P is not, the G does not preserve this uniformizer, yeah? But yeah, so you can just replace this group by this field by the one generated by by this uniformizer, and the result will be that yes, you just consider so just consider this subfield generated by this uniformizer, yeah, and
Вопрос сверху. То есть имеется в виду, что степень расширения выполнения не больше, чем степень расширения residue fields. Степень расширения выполнения — это произведение индекса ветвления и степени расширения residue fields, поэтому индекс ветвления единица.
Yes, you can say this, but you have to prove this. I mean, to prove this formula, and to prove this formula, you just look at this picture. You see, so here is the residue, the index of ramification, and we don't look at. Yeah, actually, we don't care about inertia index because here we take inertia invariance. Yeah, so actually this will be equal to 1. Yeah, and but the point is that even this automorphism group, well, when we add this uniformizer, yeah, so we assume pi, even this reduction is not injective. Is not injective. Yeah, we have to take here Galois closure. Yeah, so it's Galois closure. So this G cup of W over cup of V. Yeah, so assuming that it is ramified. If we assume this, then we get contradiction. Okay. but so how we, we still proving this, still calculating the Galois group of a single polynomial, some very specific one, very specific accent to the minus x minus 1. So now, so what we would like to say. So we would like to say that the group generated by inertia, well, by all inertia subgroup, fixes an unramified extension of our field K. Yeah. But now, we have to invoke another very important theorem from number theory. So the theorem says that there are no unramified extensions of the rational numbers. Do you know this? No? Well, что не существует неразветвленных расширений рациональных чисел, полирациональных чисел. Yeah, so theorem, theorem, so actually it is Minkowski bound, it is called Minkowski bound. It says the following, that, I'm sorry, I have to say what is a discriminant. Discriminant of a number field. What is a discriminant? Well, actually we discussed this, yeah? This discriminant is just the order of the differentials, yeah? Yeah, so...
Извините, у нас получается, как вы доказали?
Пока что ничего не доказали. Что?
Мы еще пока не доказали.
А что именно? Короллари нет. Короллари, как бы мы его настолько доказали, насколько доказали это. Потому что, you see that if it is an unramified, you see that invariance of a single inertia subgroup is unramified over restriction of this evaluation to the base field. Yeah. So if you consider a subgroup generated by several inertia subgroups, then of course it is unramified over restrictions of each of these variations. Yeah, so it's not a problem. So maybe I should say in very down the earth terms what is a discriminant, just to make sure that it is not it's not very. I don't know which kind of definition do you prefer, but so far we had what? We had definition of discriminant as a norm of certain. Yeah, we have defined discriminant as a norm of what? Of annihilator of the modulo of differentials. Yeah.
Там вопрос зал.
Какой?
Есть пример, где фактор группы разложения по группе инерции не совпадает с группой автоморфизмов расширения residue fields.
Группа инерции это ядро вот этого. То есть да. То есть это it's the kernel. So you take the decomposition group and in a sense restrict it to the residue field. So the kernel, the kernel is inertia. Пример, когда не совпадает. In our case, no. In our case, it coincides. In our case, I mean, in the case of number fields. But in general, I'm just not sure. I think you need some assumptions. For instance, even the extension of residue fields may be non-separable. So it might be. You see that even if this extension is separable, the extension of residue fields need not to be separable. But of course, this is not an example because this here I write only automorphism group, but not a Galois group. But still, just a little bit. Well, I'm not confident about that. Yeah, then I just formulate theorem and several theorems without any without any comments. So yeah, so first of all I write certain inequality. So we assume that K is a number field of degree n, and n is R1 plus 2R2. So R1 is the number of real embeddings. R1 is the number of real embeddings, and 2R2 is the rest. So it's a number of embeddings into R, and 2R2 is the number of embeddings, complex embeddings that do not pass. You see that any number field can be embedded into the complex numbers. And some of these embeddings factor through real numbers. But those embeddings that do not factor, they split in pairs. So you have an embedding and a complex conjugate. So that's why 2R2. And now the equation, inequality. So inequality, Minkowski inequality, that the square root of discriminant is, so what is, maybe I should write this, recall you that discriminant is, well, maybe I don't want to define discriminant, so let us assume that this is just well, something we don't really care about. We care only about whether this discriminant can be equal to 0, equal to 1. Yes, we do care whether the differentials are 0 or not. So because actually we didn't discuss this, but the ramification actually can be expressed in terms of differentials. Yeah. So so this is okay. Now so the inequality looks as follows. It is pi over 4 to the R2 n to the n over n factorial. But for us it's sufficient to assume we need even weaker inequality n to the n over n factorial. So what you see that it's what we need to know from this inequality is that this is always, you see that it grows, yeah? It grows because n to the n grows faster than n factorial. You see that this is pi is less than 4. Do you know this? It's important. So in principle this decreases, but altogether this grows. Yeah, and even if if n is equal to 2, here we get, what is this? This is pi over 4, here 2 square over 2, so it is pi over 2, yeah, 1/2 of pi. And what is important is that it is greater than 1. And therefore, discriminant of any number field except q is greater than 1. And this means that any extension of q is ramified. So there is at least one relation where it ramifies. Yeah, and so the conclusion with this in mind. So the conclusion is that corollary that for any Galois extension, well, any Galois, for any Galois extension k over q, the Galois group of k over q is generated by inertia subgroup. Inertia subgroups. Okay, and now it remains to show that in our concrete case, these inertia subgroups are how they are called, как они называются, эти, которые transpositions, yeah, transpositions. Yeah, so in our case, so what does it mean that we what are ramification points? Ramification points, you see that these are those points, so ramifications, these are primes, p primes, such that the polynomial x minus 1 and its derivative have common 0, yeah? And x minus 1 have common 0, yeah? So there's some places where this polynomial has multiple roots. Yeah, so we take derivative, have common roots, modulo p. Okay, so now we see that actually we can find this. So what is if x, well, maybe a common root alpha, yeah? So if this root is alpha, then we can rewrite this, yeah? So x to the n, x minus, what is this? X minus 1, yeah? X minus 1, x to the n minus 1 minus 1x minus 1 is 0, yeah? Yeah. So we want to, is it correct? Mm-hmm. Yeah. So what is written here? Here it's written, what is this? This is 1 over n minus 1 x. Yeah, because this is 0. And the conclusion, we don't really need this value, so we just want to. Что?
Because alpha is root of n minus.
Yes, it is a root of both of them. Yeah. So the conclusion. Sorry. Yeah. And the conclusion is that.
Вот мы взяли производную, да, как мы из нее получили получили...
We just
Как мы переход вот этот совершили? Еще раз.
you see that this is 0. So x to the n minus 1 is 1 over n.
Мгм.
It's written here.
Окей.
We don't need this condition. The only thing we need is that modulo p, this polynomial has n minus 1 roots, distinct roots, and one double root. And this means that, what does this mean? This means that inertia fixes all, n minus 2 roots, and this is alpha, yeah? And inertia, but actually you see that decomposition group fixes all these, inertia subgroup fixes all these elements, but these two, it interchanges, because these two that become the same root modulo p. You see that actually we have how many? We have n roots, and modulo p we have. Сейчас, простите. Алло? Да. О, сейчас, ну уже скоро, сейчас. Yeah. So we almost finished. Yeah. So you see that the point is that we have n roots, and all n minus 2 of them are fixed, and 2 of them that become the same modulo p. So this is exactly what does it mean that this is an inertia subgroup. This means that this involution is in the kernel. Yeah. So it is fixed. It is trivial modulo p, but of course it interchanges. It is a non-trivial element. It interchanges two roots. Yeah. So that's the reason. Yeah. Well. So. Thank you. Правильно. Они разные. Просто они